The breeding value prediction module of the TLR course at the University of Pretoria. We will kick off with part 1 with the basic way on how models are constructed using matrix algebra. Now that you have been exposed to matrix algebra, this will then assist you to construct these models, construct these matrices, and calculate in a very basic way breeding values so that you can get used to or get the grips of how breeding values work. We would then like to kick off with just starting with a basic model. The basic model describing the variation in recording or measurement or observations that one gets when you compare animals. So as you all know, the fundamental equation in breeding would be P equals G plus E, and then one also sometimes have some sort of error or unknown variation that you cannot fix to one of these effects. So basically the variation that we observe or measure in animals within a group of animals are basically then the result of the genetic differences amongst those animals, or the genetic variance amongst those animals, plus the environmental effects on the phenotype or the observations that we have or that we observe on animals. So this is the most fundamental equation in animal breeding, and basically describes all variation that one observes amongst in nature amongst living organisms. One can also rewrite that y equals mu. That is the environmental effect or the average effect of the environment plus the genetic effects of animal I, plus then the residual error or those unknowns that we don't know. So this is basically then the record J of animal I, and like I said, this would be the known fixed effects or environmental effects that will have an effect on the variation in performance of the animals, plus then the combined effect, genetic effect, or the genome of each animal. So obviously we know that this variation can be caused by additive genes or additive genetic effects, dominance, and epistatic effects of animal I. So if we get back to this basic equation, so the observed and measured differences amongst animals are, like we just said, are the result of the variation amongst animals in terms of the genetic effects and what we also could call fixed effects or environmental effects. The environmental effects or the fixed effects can also be subdivided into different types of effects. One of these effects, very important, is what we call the herd, year, season effects. So that means the herd that the animal is being observed in or recorded in will obviously have an effect. It can be a environment where there's it could be sweetveld or sourveld or bushveld or whatever the case might be. So that herd will have an effect. The year will have an effect. Obviously rainfall, temperature, and the rest of it, how much grass is grown early in season and so forth. So the year will have an effect, and also seasonal effect. Is it winter calves or summer calves, early spring calves, late spring calves? So all these HYS, herd year seasonal effects. Also the management group. So if you are a manager of a herd or a flock, and you manage some of the animals different to others, maybe restrict them to certain camps and so forth, or it could be animals that you give extra supplement, maybe first calvers or virgin ewes, lambs, and you feed them differently, obviously there will be a management group effect. And then other so-called fixed effects or environmental effects will be the sex of the animal. We know that males grow faster, for example, than females. A bull calf will be heavier at weaning, for example, than a female. It's not because of their genetic differences, but purely because of the hormonal differences amongst them. The age of the animal, a younger animal will weigh less, simply because that animal hasn't had the length of time to grow in. So these are all then so-called fixed effects or environmental effects. So if we were to construct any models that will predict the genetic merit of an animal, we must take cognizance of these so-called fixed effects or environmental effects, because that cannot be transferred to the next generation. Only the genetic differences amongst the animals can be transferred. So within the genetic effects, we obviously, it should be known to you by now that you would have the effect of additive genes, many genes, each with a very small effect. They add up to the total breeding value or genetic merit of the animal, and so-called non-additive effects like dominance or epistasis. We also know that that is just by chance, where you have a combination of two alleles having a non-additive effect. So that will have an effect on the performance or the P of the animal, but that you have no guarantee that will also be transferable to the next generation. So what we actually want to know if we predict breeding values is the additive effect. So per definition, the additive genetic effect or the additive genetic makeup of an animal is per definition also the breeding value of that specific animal, or the value of the animal as a parent in the next generation. Good. Like I said, that is then the breeding value. So if we construct these models, we would like to, I would like to say, isolate the additive effect, because that would be the value of the animal as a parent. And our models need to take all these other effects in consideration so that we end up only with the additive effect in the end. Good. So just a very simple way that one can also describe the breeding value would be where we only have phenotypic measurements. So we don't take any other factor in consideration. We have, let's say we have a group of 10 animals or so, and we weigh them. Let's say it's beef calves. We weigh those calves. They're all of the same. Let's say they're all of the same sex. They're bull calves. We weigh them in a group, and we want to predict just based on those weights. We want to predict the breeding value of those animals. Obviously, we know that that might not be a very accurate way of dealing with breeding values, but that's one way one can use in a very simple way to predict the breeding value. So the actual observation or the breeding value of an animal I, equals what we call a B, we'll just get to that, multiplied by the actual weight of the animal or the observation of the animal minus the average of the group effect. So just to be practical, if the group weighs 200 kilograms on average and a specific calf's weight is 210 kilos, so that would be 210 minus 200, that would give you 10 kilos, multiply by something. That something then in animal terms or animal genetic terms would be your heritability of the specific trait. So it's the additive variance divided by the total variance, and that would give you the heritability in the narrow sense, because that is the part that can be transferred to the next generation. So if we come back to our example, if this specific animal weighs 10 kilograms more than its contemporaries or the average of the group, and the heritability is 0.5 or 50%, and it weighed 10 kilos more than the group, the breeding value will be 0.5 times 10, and that would give you half of 10. That would be plus 5 kilograms. A calf that is, let's say, 2.5 kilos lighter than the group mean, and the heritability is obviously still the same, 5 kilograms lighter, so that breeding value will be minus half of 5 kilos minus 2.5 kilos, and so forth. So that is a very simple way that one can predict the breeding value of an animal, and that is also the basic building block that we will use in BLUP. So whatever the trait is, you start with a basic building block. So you have to define the contemporary group or the environmental effect that affects all those calves, all those lambs equally. And remember, the HYS, herd year season, is a good example. Same sex, have some corrections for the age of the animal, age of dam will have an effect, and so forth. So you need to have all calves or all lambs on equal footing when you do this, and each of them will then be compared to this mean or this average of the contemporary group. So you need to know a few things. You need to have an observation. You need to have your groups well defined. You also need to know what the heritability is. Otherwise, you can't even start with a prediction of breeding values. Good. This can also be extended further, and this is maybe how this whole thing started with sex-limited traits, such as in dairy cattle, where you cannot record specific traits on one of the sexes, like you can't record milk in a bull. So, and you needed to have a prediction of the genetic merit of a bull, an AI bull, for example. So, similar to the first equations, the breeding value of a specific animal will now be the average of single observations of n progeny, as number of progeny of a specific bull compared to their contemporaries multiplied by h squared. So it's basically the same. So you have this bull with a lot of progeny groups in different environmental or progeny groups with the progeny of other bulls, and all those comparisons together will then give you a prediction of the breeding value of a specific bull. The very first example that we used, where we have observations of animals, is what we, or how the so-called animal model was developed. And this example that we're looking at currently is the very first BLUP evaluations that were developed, the so-called sire models. There are obviously some limitations in sire models, and animal models followed suit, where one add some other sources of information that enhances the accuracy of the prediction. Good. So we also have to ask some questions about the way that we just used to predict these breeding values. The questions one can ask is, what about the random sample additive genes received from parents? So in the examples we used up till now, or especially on the first one, we didn't consider the possibility that each of those animals received an additive, a random sample of additive genes from the parents, from each of the parents. So that is negated in the way that we did that prediction. The other question is, what is the effect of a specific contemporary group on the variation of the phenotypic value? So maybe where you have an environmental or an environment that is not very suited for production, you might have a bigger variation around the mean. So an animal will then, or the best animal will be very far removed from the mean and will have a very high breeding value prediction. Or the same could also be true for an animal on the lower end of the scale. So, and one could also then ask, what about the possibility that there could be a re-ranking given the fact that you maybe tested the same group of animals in a different environment? And that re-ranking would then also change the breeding value of those animals. So these are questions that cannot be answered by the simple way that we just illustrated. And then also, what about phenotypic comparison due to genetic level of peers? Here one can use the example where you have an animal better than its peers, its contemporaries, but it's simply not because it's good, it's because of its contemporaries not being that good. So basically he's the best animal in the group and therefore he gets the best breeding value, but the average of the group is so low because of low genetic merit of his contemporaries that he has to compete against. So in simple terms, this means that two animals with the same genetic merit being evaluated in two different groups, the one group being a group of animals with very high genetic merit and the other group on average animals with a very low genetic merit, those two animals will basically have different breeding value predictions simply because they were compared to animals of a different genetic level. So one have to then also, or the next developments in blood breeding value predictions has taken this into consideration. So I would like to call it the gene flow from the parents down to the progeny needs to be taken in consideration in this whole process. Good. Let's start with the mixed model equations. This is basically what we have said, that any observation of an animal or the differences in measurements amongst those animals are basically a result of the environmental or the fixed effects plus the added, in this case, the additive genetic effects, and then also residual effects. So basically, if we want to know the additive genetic effects or breeding values, we need to separate the additive effects from the non-additive effects. We can rewrite that equation in so-called matrix notation. So y equals xb. X obviously is a matrix. Remember from the matrix algebra lectures, capital, plus z, matrix za, plus then e, small e. So y is an n by 1 vector of observations. So it's a column vector of observations. B is a vector of fixed effects. So B is a vector of fixed effects. So let's say we have 5 herds, each with 2 seasons. So that there will be 5 herds, each with 2 seasons. So it will be a vector of 10 fixed effects. A is a vector of random animal effects or additive effects, and obviously A is a column vector with the number of rows equaling the number of animals. And E then, like we said, is a vector of random residual effects. So X, the matrix X, is a design matrix of the order n by p, linking fixed effects to observations. So each of these animals with a recording needs to be linked to a specific fixed effect contemporary group, for example, or a sex. If it's 2 sexes, you will have 2 fixed effects. If it's 5 herds, each with 2 sexes, it will be 5 herds, each with two levels for sex. And also, if they have 2 seasons, there will be 2 more fixed effects per herd for those herds with 2 seasons. And then a Z is a so-called design matrix linking observations to random effects. So it's basically all those animals with recordings, with observations, will have on the diagonal, will have a 1 linking the animal to an observation. If the animal does not have an observation, it will have a 0 on the diagonal. This is then the basic equation for blood breeding value models, the so-called random effects. Why random effects? Because we have random animal effects, unknown random animal effects. Each animal receives a random sample of genes from its parents. We don't know what random sample they received. That's why we call them random samples, random animal effects, but we also have fixed effects, known environmental effects that affect the animal's performance or recording. So that's why it's a mixed model. It's mixed between random and fixed effects in this model. So basically, for us to enable us to calculate breeding values, we need 3 sources of information. So at the very basic level of genetic merit prediction, or the genetic breeding values of animals, we need 3 sources of information. The first source is the pedigree of the animal. Why the pedigree of the animal? Because we know that the whole genome of each animal is a result basically from what it gets from its parents. Half the alleles from the one parent, the other half of the alleles from the other parent. So they get a random sample, but we need to then have the pedigree because that will give us the relationship amongst these animals. Relationship basically means how much of the additive genes are similar or exactly the same as that of all the related animals in a population. So that's the first source we need. The second source we've spoken about is a deviation from its contemporaries. So if we use the winning weight example again, the 10 kilograms difference, let's say an animal weighed 210 kilos and the mean of the contemporary group was 200 kilos, so that difference, that plus 10, that's more important than the average weight. And then we also need, as a third source of information, the additive variation related to the total phenotypic variation, and that is, in simple terms, is the H-square, or the heritability of that specific trait. How much of this deviation can actually be transferred to the next generation? How much of this deviation is due to additive genes and not other genes causing that? So, and that in essence is then the heritability in the narrow sense. So those are the 3 sources of information that we need to enable us to predict breeding values for farm animals. Good. So the result, or the answers, we call BLUP, best linear unbiased prediction. So why is it best? Because it maximizes the correlation between the true breeding value and the predicted breeding value. So predicted breeding value are usually written as A hat, A meaning additive genes. So A hat is our prediction, and the true breeding value is probably never known, and it's also obviously dependent on the population that it was that the progeny will be raised in. So that's where the best comes from. It's linear. These are all linear functions of observation. So we use linear equations. All these equations that we have written down are basically linear equations. So it's linear equations that we use. It is unbiased because it's free from the bias of environmental effects, and it's also free from the possible bias of mating best with best, for example. And that maybe will become clearer as we go along. And it's a prediction. It's a prediction of the true breeding value of the animal. So based on the sources of information that we have just talked about, pedigree information, observations as a deviation from the contemporary group mean, and the additive variance as a percentage or a part of the total variance. That is being used to predict how the progeny of two animals will differ in the next generation. These are the basic mixed model equations written in matrix notation. So we end up with a few matrices that will assist us. Remember, we have the number of equations. Each animal has its own equation, and we also have an equal number of unknowns. Each animal has its own equation, but each animal also, its breeding value is unknown. So we need matrix algebra to assist us in the process of solving all these unknowns, one unknown for each animal, and also to have an unbiased solution for the fixed effects, because we have unequal numbers per fixed effects. Not each of these contemporary groups have the same number of animals in it. We might have unequal numbers in terms of the two sexes, the age of dam effect, etc., etc. We also know that the actual level of performance in a contemporary group is obviously not just an environmental effect, it's also the genetic effect of the animals. So we also will get solutions, best linear unbiased estimates, blues, for the fixed effects, and best linear unbiased predictions for the additive or random effects. So these are then our matrices. This big one here is what we call our coefficient matrix. Remember the coefficient matrices from the previous lectures, in terms of when we talked about the A, B, C, and D, and so forth in that part of the matrix. Then we have a column vector. The top part of the column vector would be our different levels of our fixed effects. Let's say we have 3 herds with 2 sexes. That would mean sex 1, sex 2, herd 1, herd 2, herd 3. So then we will have 5 rows. It's obviously a column vector, so we only have one column. And then we will have a row for each and every animal that we are to predict a breeding value for, including those animals that might not have an equation, because might not have might not have a measurement, but they will have an equation because they are related to animals that have measurements. Like the example we used, where we have an AI bull, let's say a Holstein AI bull. No observations were possible on the bull itself, because you cannot measure milk on a bull, but it will have related females with observations in their contemporary groups. And then we typically have what we call the right hand side. On the top part here we have the combined effect of the fixed effect. So if we have 2 sexes, that would be then added, or the summation of all of sex 1, let's say it's female sex 1, the summation of all the weights of the females, and in the next row we will have a summation of all the weights of the males. And if, for example, we have 3 herd effects, herd 1, 2, and 3, we will have the summation of the weights in herd 1, herd 2, and herd 3. So that would be the top part here, x prime y. The bottom part here of our column vector would be the actual observations of the animal. So basically, if an animal weighed 214 kilos, there will be a 214 kilos. If there's no weight for the animal, that would be blank. So this is then basically how the mixed model equations are being constructed in terms of matrices. That brings us to the conclusion of our first part of breeding value predictions, the breeding value prediction module of TLR at the University of Pretoria. Part 2 will follow on this.